Hello students, this is lecture 7 of MTH 201. In the last lecture we discussed quadric surfaces, graph of a function in space in R3, level curves and level surfaces. There was missing information in slide 7, lecture 5, which is when we defined velocity of a path. So when we define velocity of a path c at time t, it's given by this vector which is limit, right? So it could be the case that this limit does not exist. So we define velocity to be this vector provided the limit exists. Okay. So I did not include this in the notes that time, but this is something that you need necessarily. This velocity vector will only be defined if this limit exists. Okay. So today we are going to focus on functions of two variables primarily and define the notion of partial derivatives. So recall when you have a function from an interval to r, so function of one variable, you already know the notion of differentiability of this function at a point. Right? So if I start with a point x naught in this interval, I say that f is differentiable at this point if this limit exists, which is the ratio of f of x naught plus h minus f of x naught divided by h, which is nothing but the rate of change of f at the point x naught, right? And geometrically this was nothing but the slope of the tangent line at the point x naught comma fx naught on the graph of the function f, right? And it had several notations. The first, I have listed several that are used generally in books. So df dx at the point x naught, df dx, you draw a vertical line, you write x equal to x naught, f prime x naught, or f to the power 1 in the bracket x naught. And for higher order derivatives, you put a k here and k on the bottom, and in the last notation you, instead of 1 you put k, and in this third notation you put that many primes, which is not very convenient if k is large. So all these three notations are more convenient when you look at k which is not equal to 1. Okay. So now let us generalize this idea to higher dimensions, but there is a problem there. It doesn't work directly. So we have to first define what are called partial derivatives of a function of two variables. Let us first define it with respect to x. So you can calculate partial derivatives of a function with respect to any of its variables. So in this case, I am taking a function which is defined on R2 to R. It's a function of two variables x and y. The partial derivative of f with respect to x is calculated by treating the other variable y as a constant and differentiating f as a function of x alone. Okay, like a function of one variable. So you treat y as a constant and you differentiate with respect to x. Okay. So if I take a point x naught, y naught in R2 and you consider this limit is very similar to what we saw earlier. The difference is now f acts on two variables. You keep the second variable fixed, which is the point that you start with, so y naught, and you vary the first coordinate, right? So this is like if I ignore the y naught term, then it is like differentiating in the first coordinate, right? And evaluating at the point x naught. So if this limit exists, we say that the partial derivative of f with respect to x exists at the point x naught y naught. Okay. Now note that this limit is nothing but the derivative. Okay, so if I think of now f as a function of x alone by putting y equal to y naught, then this is this limit is nothing but this, right? You look at the function f x comma y naught. Remember, y naught is fixed. So f x comma y naught is a function of x alone. You differentiate with respect to x and you evaluate at x equal to x naught. This is basically the definition that we saw on the previous slide. So what is partial derivative? Partial derivative with respect to x at the point x naught y naught is not is nothing but the derivative in the one variable case that we saw with respect to x by putting the other variable to be equal to the value. Again, there are several notations to denote these partial derivative if it exists. It's denoted as del f del x at the point x naught y naught. So instead of d, we use del to denote that it's partial, it's not full derivative. Then you can also write it like this, or f sub x, x naught y naught. This is the most convenient notation because you don't have to keep on writing del del and so on. So you write f sub x if you are differentiating with respect to x. And you can also talk about higher order derivatives where you, like in one variable, how do you get the second derivative? You differentiate once and then you differentiate again. So similarly here you differentiate k times, meaning you compute the partial derivative with respect to x once, then twice, and k times. That will give you this answer. And you put this limit in the end. You put x naught y naught in the end. You don't put it at every stage because then it becomes a constant, right? And constant derivative will be 0. So when you put, like in one variable case, you put this point at the last stage. You can also write it as f sub x x x x k many times, how many ever times you are differentiating at the point x naught y. This is derivative with respect to x. Similarly, you can define derivative with respect to y where you treat x as a constant. So now you put x naught as it is and you vary y. Okay. So you are writing y naught plus k minus f of x naught y naught divided by k, limit k goes to 0. If this limit exists, then we say that the partial derivative of f with respect to y exists at the point x naught y naught. Again, this limit is nothing but the derivative of the function of one variable, which is f of x naught comma y at the point y equal to y naught. Okay, so this is very similar to the previous slide. In the previous slide, we were treating y as a constant and differentiating with respect to x. Here, we are treating x as a constant and differentiating with respect to y. Again, the only difference now is x is replaced by y. So these are the notations. And you can also talk about higher order derivatives. The first two are where you are only differentiating with respect to y. But in the in the third and the fourth, you can also differentiate both with respect to x and y in some certain order. So I will not talk about this at the moment. We will come back to this again. Okay. But this you understand. The first two you understand. Okay. So now you can generalize this idea to function of more number of variables, not just two. So if you have a function which is on n variables x1 through xn, you call the partial derivative of f with respect to a variable xi by treating all the other variables as constant and differentiating with respect to xi alone. So here I have put this xi plus hi in red just to catch your attention. So if you are differentiating with respect to xi, you keep everything else fixed, you only change this term. Okay, and I have used h sub I just to emphasize that I am changing the xith term. Okay, there's nothing great about hi, it's just a notation, it's just a number that's going to 0. So if this limit exists, we say that the partial derivative of f with respect to xi exists at the point x1 through xn. And again, notations are quite similar. Then you have higher order derivatives, which as I said, I will come back to it later. But at least you should be able to make sense of this notation, right? You are differentiating partially f with respect to xi. You can write it like this in the del notation or f sub xi. Okay. So now let us look at a few examples. So let f of x comma y be x squared plus 3y. Then what is fx? Remember, for fx you think of y as a constant. So the second term is a constant. So differentiation is 0. So you only differentiate the first term, which gives you 2x when you differentiate with respect to x. Similarly, fy would be treating x as a constant. So this term x square is a constant. So derivative of that with respect to y will be 0 and you will only get 3 when you differentiate 3y with respect to y. Now what is fxx? It is differentiating fx with respect to x. So fx is 2x. Now there is no y already, so it's easy. So when you differentiate with respect to x, you just get 2. Now fy is 3, which is already a constant. So when you differentiate fy with respect to y, you just get 0. Now when you take fxy or fyx, that is nothing but differentiating fx with respect to y or fy with respect to x. In both the cases it comes out to be 0, right? Because fx is 2x, there is no y, so when you differentiate with respect to y, now you get 0. Similarly, fy is a constant, does not depend on x, so if you differentiate with respect to x, you get 0, right? Now, if you evaluate at the point 1 comma 2, then fx at 1 comma 2 is calculated by looking at fx and putting x equal to 1 and y equal to 2. So when you put x equal to 1 and y equal to 2 here, there is no y, so it doesn't matter, you just get 2. And the value of all other derivatives indicated above are independent of the point since they are already constant. So we don't even have to consider them. So at all the points they are what they are. Let us look at this example, x square plus 3y, where there is an extra term which has a product of y and z. So if you calculate fx, it comes out to be 2x, right? Because these terms, second and third terms are constants. Fy, first term is a constant, second term with respect to y gives you 3 and third term with respect to y gives you e to the minus z. So you get 3 plus e to the minus z. Now with respect to z, first and second terms are constants, the third term will give you negative y e to the minus z because derivative of e to the minus z with respect to z is this, minus of e to the minus z. Now if you put 1 comma 2 comma 1, then the values come out to be, if you put x equal to 1 you get 2, z equal to 1 you get this, and y equal to 2, z equal to 1 gives you this. And higher order derivatives can also be computed similarly. An observation in these examples, these are called mixed partial derivatives, where you differentiate with respect to more than one variable. So in this case, fx y f by x, fxz fzx, fyz fzy, wherever they are possible. Like the second and the third is not possible in the first example because there is no z. Now in these cases all these mixed are equal, and this need not be the case all the time, and we will revisit this issue of mixed partials later. Okay. But what happens is all the nice functions, these are very nice functions, right? Polynomials, exponentials, maybe trigonometric, they are all very nice functions and they have such properties. Okay. A notation. So if z is equal to fxy, then f sub x can also be written as z sub x. So whatever the z is, and del z del x. Similarly, fy can be written as z sub y and del z del y. So these are some other notations that we might use. In general, if u is a function of n variables, x1 through xn, then we can use del u, del xi, uxi and so on. Okay, right. So now let us talk about geometrical interpretation of partial derivatives. Okay, this is very important. So remember, what do we do when we calculate partial derivative with respect to x? We treat y as a constant, and which constant? At the point x naught y naught, we set y equal to y naught. Now in R3, what is y equal to y naught? Y equal to y naught is a plane that is parallel to the xz plane, right? Passing through, right? Uh, it's parallel and passing through the point y equal to y naught, right? So this is, so when you look at this plane, right? This plane, yeah, this one, the the one that is facing you, this one, that's the plane y equal to y naught, right? It passes through this point x naught y naught. So when you look at the graph of this function fxy and you intersect it with this plane, you get a curve, right? That curve lies on this plane y equal to y naught. So what is partial derivative now? Now this is a curve that looks like a curve in one, for a function of one variable, right? So you look at this curve and you look at this curve and you look at this point x naught y naught and you look at the tangent line. So the slope of that tangent line is nothing but the partial derivative of f with respect to x at that point, because you were looking at y equal to y naught plane. Now, for partial derivative with respect to y, you look at, remember we put x equal to x naught, right, constant. So what is x equal to x naught? It's a plane which is parallel to the yz plane, right? So this slanted plane is basically x equal to x naught. Again, when you intersect this plane with the graph of the function, you get a curve, this curve. Now this curve at this point has a particular slope, and that slope is the partial derivative with respect to y of the function at the point x naught y naught. Okay, so that's how you understand partial derivatives geometrically. So let me say it in words. So if you have a function f from R2 to R, a function of two variables, the graph of the function is the collection of points x, y, z in R3 where z equal to fxy. So this is what we plotted here, right? This is the graph in R3 where z equal to fxy. You fix a point P naught, x naught, y naught in R2 and you consider the plane passing through P naught and parallel to xz plane. So I should have been careful. This plane doesn't pass through p naught. It passes through actually x naught, y naught, f of x naught, y naught, right? Plane parallel to xz plane. So this is the plane y equal to y naught. Now this plane intersects the graph of the function f in a curve, right? What is the curve? The curve is nothing but f of x comma y naught. Remember y equal to y naught. Now this is a function of one variable, x alone. So the slope of the tangent line to this curve at the point x equal to x naught is given by this derivative, which is equal to the partial derivative at that point, right? This we saw in the while defining the partial derivative with respect to x. Similarly, if we consider the plane passing through P naught and parallel to yz plane, that is the plane x equal to x naught, and this plane intersects the graph of the function in a curve which is given by f of x naught comma y. This is a function of y alone where x naught, x coordinate is fixed. The slope of the tangent line to this curve at the point y equal to y naught is given by this derivative, right? Because we are differentiating with respect to y, but on the slide where we define partial derivative with respect to y, we noted that this is nothing but the partial derivative of f with respect to y at the point p naught, which is given to, right? So therefore, now you understand what is the geometrical significance of partial derivatives with respect to x and y. Okay, and this can be generalized to higher dimensions as well, where of course one can't draw geometric figures, but one has a sense of what these partial derivatives mean. Okay, so let us stop here.